For this video, we are going to take a look at slope fields and Euler's method. And I like to, when I teach or talk about slope fields, I like to come back to the idea of topographical maps. We do a lot of backpacking and camping in our family. And slope fields are very similar to these maps in the way that they kind of map the way that the mountain is moving at certain levels of elevation. So it's going to be similar. Some of the slope fields that you create will be similar to that. Actually, a more realistic depiction of slope fields would be weather maps. So if you look at wind and wind changes, velocity of the wind, the speed of the wind, in other words, and the direction of the wind, that would be a more accurate depiction. But I like looking at topographical maps when I talk about slope fields. All right, so first of all, a couple definitions. We have general solutions and particular solutions of these things called differential equations. If you have been watching my videos, you've learned, we've talked about differential equations and even solutions of differential equations, but this is just to serve as a quick review of those things. And so a differential equation is easily just defined as the equation of the derivative But remember, in calculus, yes, we study the derivative, but at the same time, we also like to think about the derivative as change, especially when we're answering questions or solving problems. So we're going to say it's the equation of the derivative or change. All right, so that's what the differential equation is. So it would be given in the form of dy dx or y prime. Both of those mean the equation for the derivative, which represents the change of the function. And the change, understanding the change, and that's the same thing as the slope, is extremely important when we're talking about slope fields. Now, a solution is a function that is called a solution of a differential equation if the equation is satisfied when its derivatives are replaced by f of x and its derivatives, right? So I'm going to write that down so that you can copy it. So a function is called a solution of a differential equation if the equation is satisfied. So if the solution is satisfied when its derivatives are replaced by f of x and its derivatives. Now, what exactly does that mean? That is a great question, and I know you were asking that, so let's try an example of determining exactly what that does mean. So in this question, we have y is equal to negative 2 to the x, and that's the original function. That's the f of x. And here's your equation for the derivative. How do I know it's the equation for the derivative? Well, look, right here you have y prime. Therefore, it is the equation of the derivative. That is your differential equation. Well, it also says in front of it, I guess, huh? All right, so first of all, to confirm, we are going to go ahead and find the derivative of the original. And finding the derivative of e to the negative 2x, you would multiply by the derivative of negative 2x. That would be negative 2. E to the negative 2x. So that's your derivative. Now, what we're going to do is we're going to make some substitutions, right? So we know that this is the derivative. So we're going to plug it in right there. We also know that this is y, so we're going to plug that in right there. So try this on your own. Make those substitutions and then come back to the video to see if we come to the same, if we get to the same result. You make those substitutions, You plug in the y prime there, and then your y right here, and then you distribute. Right, well, there's just a 1 in front of there. And then when we put these together, 6 negatives, 5 positives, it does, in fact, equal that side. So it checks out. That is us verifying that that is entirely true. Okay. Now for the next one, it says determine whether the function y is equal to 2 sine x is the solution of the differential equation. Now we know that's the differential equation. This is not y to the fourth, right? That means the fourth derivative of y. All right. And the only way I know that is because it says a differential equation and it's in parentheses, so that helps us understand that as well. So that's the fourth derivative of y. All right, so that means you're going to have to go through and find the first, second, third, fourth derivative of y to answer this question. So try this one on your own. Pause the video, try it, and then come back and see how you did. So we should have, when we go through and find these derivatives, you should have that the fourth derivative is going to be 2 sine of x. And I substituted that in up here for y to the fourth derivative of y, which is right here. So it's the fourth derivative of y minus 16 times y, which again was the 2 sine of x. But we can stop there because we know that that's not going to equal 0, so we cannot verify. So it does not satisfy. Okay, that differential equation does not satisfy that function. All right, so that's what the solution means. What about the general solution? Now, the general solution is something like the family of functions. If you think about what we're doing when we are integrating, right? The general solution includes every possible solution. Every possible. To every possible solution to the differential equation. You know, for example, when you were doing like, if the differential equation was x 3x, I don't know, 3x squared plus 2x plus 4, right? When we find the derivative, or not the derivative, but we integrate, right? We add 1 to the exponent, so that'd be to the third, divided by 3, so that would just be x to the third. Add 1, that'd be 2, divided by 2, so that would just be x squared. And then this is x to the 0, so you'd add 1, so that would be plus 4x. And then you'd always have this plus c, and that is the part that makes it the general solution, right? Because what does that plus c mean? You learned back in Algebra 1 that moves it up and down vertically, up and down your x-axis. And so it's similar to the idea of the family of functions in that way. Right, so we've been finding general solutions. We've been also finding particular solutions, and that's where you would find it at we are given a specific point, right? So particular solution is a specifically defined by a point. Usually by a point. A. So it's specifically designed solution. So sorry, A specifically defined, usually by a point, solution to a differential equation. Okay, and that specifically defined solution, or that point, is called the initial condition, and the initial condition is used to find particular solutions usually a point on the graph of the solution. So these are used to find particular solutions. Usually at a point on the graph of the solution. And we're going to do a couple examples kind of showing how to use those initial conditions to find the particular solution, the exact solution. Okay, so showing that, so findings given initial, this is an example. We will do an example. This is another way of verifying, sorry. This is another verification. If you want to go ahead and try this one, we'll do this one really quick. This one isn't too difficult. This is like what we did up here, just verifying those solutions. And I will work into finding particular solutions in these next couple of examples, what that means. But go ahead and try this one right here. Oops, this one right here. Verify that. So pause the video, try it, and come back. You do show that it verifies, because when we find the derivative, you get x plus 2 sine of x. So we're going to plug it right in there. So x plus 2 sine of x is equal to, as you can see, x plus 2 sine of x. So we verified that that is the solution to the differential of x plus 2 sine of x. Okay. That's very straightforward. Just wanted to do one more example, but getting into, again, we will do an example here, finding particular solutions with an initial condition. But looking at slope fields, we talked about how it's like a family of functions. And so hopefully I'm going to show you some pictures of slope fields, and we're going to construct part of a slope field so you can kind of make that connection to the idea of the family of functions that you learned in Algebra 1. And it's rather cool if you think about really what we're doing, using the differential without even knowing what the original function is, because sometimes you can't integrate a function, but you can determine exactly what it looks like graphically without the original function just by using its slopes to construct that piece by piece. Okay, so first we're going to sketch the slope field for that differential equation, and then we want to determine that initial condition, the 1, 1, we want to draw a graph through that point. Now I'm going to be honest, this is a lot of work, okay? I'm going to show you how to kind of some shortcuts that you want to look for to make this a little bit easier, because in this case in particular, you notice in your differential equation, right, there is no y variable. And we're going to look at what that means when we construct the differential equations. Let's set up our table. Now your table, you can set up a table however you want, but I'm going to do a horizontal table using rows for x and y, and I'm also going to include a row for y prime. Table, just to get an accurate depiction, I'm going to go from -5 to 5. Now this could be a lot of work, but remember, one thing that you could do to make this a lot faster is you could actually plug this into your calculator. So in your calculator, it would be y equals, right? And then you could come up with a table, and because the only reason you could do this in your calculator is because there is no y value. So what these are really doesn't matter, okay? If there was a y on the other side, then you couldn't do that, because then you would technically have 3 variables. You'd have x, y, and y prime. But there's only 2 variables. So plug this into a calculator, and then you can easily get the rest of your table. And then when we do that, I'm going to fill in the rest of these real quick on y prime. So if you want to go ahead and try that, see how you do. That we have our y prime values. Again, y doesn't matter. And what that means, since y doesn't matter, right? So since there is no, y, in the equation of the derivative, the differential equation, y prime, right, the slopes are the same vertically. Okay. So if we look, so at x equals -5, I'm going to kind of zoom in here. At x equals -5, we're just going to go right across the x-axis. At x equals -5, the slope is about 10.8, so it's super steep. Okay. X equals -4, the slope is 7 1/3, a little less steep. And then 4 1/2, a little less steep. 2 1/3, a little less steep. And then 0.8, just under 1, and then at 0, it's 0. Straight across. Now, if we wanted to, you could go ahead and, since those are all the same vertically, what we're going to do at each point is we're just going to put a little dash to represent the slope at that point. So this is a little less, a little less, a little less, and 0. Okay, so you can kind of see how it's curving, and they're also going to look like that down. Okay, so I'm going to go ahead and pause the video and finish up this half of this slope field, and you do the same on your end. At 1, it's barely negative, right? So it's not 0, but it's negative, so I'll just do that. We can do that up and down, but I'm going to pause the video when I go to do that. Then here, it goes at 2, it goes to 1/3. So it's something like that. And then the 1.5. And then it starts getting steeper, steeper, and we only went out to 5. So I'm going to pause the video and finish these vertical slopes, and we'll look at what the graph looks like. Is what our slope field graph looks like from -5 to 5. Again, this was easy to compute over here because there's no y. So vertically, they're all going to be the same. Sometimes they're not going to be the same vertically, sometimes they'll be the same horizontally, or sometimes they'll be different, and we'll look at some of those as well. We won't actually sketch them, but we'll look at them. Right, so that's how you construct a slope field. Now, what we're going to take a look at is we're going to look at the initial condition passes through point 1, 1. Let's go ahead and put a point on our graph at 1, 1. So we come over here, x equals 1, y equals 1, boom. Essentially, we want the graph that goes through that point. And that's the cool thing, is that that will give us the original function. So if we know what the derivative is, or the differential equation is, but we can't find the derivative, the integral of that, but then we can construct a slope field to determine what the graph looks like. We don't necessarily know what the function is, but we could determine what the graph looks like. Okay, so let's go ahead and find the exact solution. Or the particular solution, whatever you want to call it. Right? So, okay, so first of all, we know that our derivative is 1/3 x squared minus 1/2 x. And when we integrate that, since it's one that we can integrate, that's where we can find the exact solution. Otherwise, we wouldn't be able to. We could kind of get what the graph looks like. We know that f of x, or y, that's the original function. When we integrate the derivative, you get 1/9 x to the third minus 1/4 x squared, this is a 4, plus c. And that c means we have the general solution there now. But if we want the specific solution, we need that initial condition, which we were given at 1, 1. So we're going to go ahead and plug 1 in for y, 1 in for x, And we can solve for C. Whoops, this is 1. Put a 1 in there. And we can solve for C. When we go through and do that, you would get 1 is equal to, in order to add these together, you would have 4 over 36 minus 9 over 36. And then you would end up getting a negative 5 over 36. Add that over, you would get 1 in 5/36. And for this case, since we're going to graph it, I'm going to change this to 41 over 36. And so our exact solution is y equals 1/9 x to the third minus 1/4 x squared plus no longer c, sorry. We know that c, what that c is. It is 41 or 1 in 5/36. Okay, that's the exact solution. And so what that should do is when we graph it, it should go exactly through. And we can sketch it here, but I'm going to show you on the graph. It's kind of ugly, but it looks something like this. Kind of follow those curves around. And we're going to take a look at what this actually looks like on a graph. So here we have our slope field. And you can see it's very similar to the one that we just drew. This goes from negative 10 to 10, and it looks very similar to the one we just drew. And let me go back to that one to show you. Right here. Okay, it's actually pretty good. Now, what I'm going to do is I'm going to go ahead and graph the equation that we just came up with. So here we have 1/9 x to the third minus 1/4 x squared plus the 41 over 36. We're going to go ahead and graph that one. Boom. And you can see it's going to go right through. Oh no. I made it disappear, but here we go. It graphed, and you can see it goes right through, and the cool part is how it follows those slopes. So the slope field, that was generated by the equation for the derivative, right? And so here are all of the derivatives that we got. And we then construct a graph of the original by using that slope fields through a particular point. So it's kind of cool. Okay, so anyway, so that is up here. I told you finding particular solutions. This is exactly what we did. We found that exact solution given our point 1, 1. So enough about slope fields. Let's see if you can go ahead and just match these slope fields with their differential equations below. Think about the shortcuts that I talked about up above on the previous problem. You know, if there's no y, the slopes are the same vertically. Well, I'm going to tell you if there's no x, the slopes are going to be the same horizontally. So use those ideas. You will have to do no math via if you understand what that absolutely means. Try these, come back to the video. First one, you notice there are both x and y in that differential. There is a both x and y in that differential, so we're going to go ahead and just set up a table. This time I'm just doing a vertical table. I'll show you it doesn't really matter. When x is -2, let's say y is -2, so we'll do the diagonal. Y is -2, -1, 0, 1, 2. That will give us that diagonal that goes from left to right on that graph. And we're going to look at that diagonal to make sure these slopes are the same. And that actually works out really cool here because x and y are the same. That means your slopes are going to be 0. So at that y equals -x diagonal, those slopes should be 0. So if you look at these, okay, at this, nope. Yeah, look at that, right? Those slopes are 0. So 0, 0, 0, 0, 0, 0, 0. So we know that this matches figure B. And then for the other two, if you know enough about, remember I talked about if there is no y, then the slopes are the same vertically. And if there's no x, the slopes are the same horizontally. right? So on A, they are the same vertically, meaning when you go up, they are the same. And then on C, they are the same. So this is C, and that is A. So because on C, they are the same horizontally. So this is fairly easy if you know some of those shortcuts to understanding those slope fields and their graphs. And the last thing we're going to talk about is Euler's method. So before we do this problem, I forgot to leave room for the actual equation for Euler's method, which will be a little bit different than what you see in some textbooks, but the equation for Euler's method, I'll just put it down here. Because what Euler's method does is it approximates the solution of a differential. We are not finding the exact solution. We approximate the solution given step sizes, right? So in this case, the h is 0.05. And in my equation, I use h. Instead of h, I use change in x because it's the same thing. All right, so here's the equation. To find y sub n, you would take y sub n minus 1, so the y before it, plus the change in x times. Now this next one's kind of hard to do. Now n is the number, how many steps, right? And so inside this x, since it changes, it's going to be whatever your x was times your, I said maybe your n times change in x. Now, when we do this example, maybe that'll make a little bit more sense. Some of the books have maybe this a little bit different, but this book makes sense to me. And then y sub n minus 1. And with this, remember, this is, if your change in x is 0.05, every time you're adding 0.05 to the x before it. All right, and so that's how you would find those x's. And again, that gives you y sub n. Now let's apply this to this problem here. Zoom out a little bit. We're using Euler's method to approximate the solution of the and we're not going to use a table of values. I don't like table of values. And we're only doing 5. In the books, they have you use more, but we're only doing 5 because I think there are calculator programs that do this, but we're not going to do that. We're only doing 5 steps. And we need to start with y sub 1. Okay, that's our y sub n. Is equal to y sub n minus 1 would be y sub 0. That would be your initial condition right here, so that would be 2. So y sub 1 is equal to y sub 0, which we just talked about was 2, plus the change in x right here, that 0.05, times, so our x, right, our very first x, so this would be x sub n minus 1. Our very first x was 0 in this case, that makes it easy, plus y sub n minus 1 we already used right here is 2, and we know up here as well is 2. Then we go to just plug that into your calculator just as it is, however you want to do that, but you would get 2.1. So that is your y sub 1. And then we're going to start using y sub 1 and finding the second one. We'll do this 5 times. So then it would be, instead of 2, it'd be 2.1 plus our change is always the same. And here's where this comes in. So you're going to add the change to this, which is be 0 plus 0.05, which is 0.05. Plus our new y, which is 2.1. Plug that into a calculator, and you get 2.2075, 2.2075. All right, so that's your estimate after 2 steps, and we're going to do 5 steps. So go ahead and do 3 more steps to get you set up for the next one. We would use that new y, so 2.2075 plus yada, yada, yada. Everything else stays the same pattern, I should say. Go out to 5 steps and get that approximation. So pause the video, try this, and come back. And check to see how you did. And as you're getting these new y values, right, I always tell students to round to the thousandths place. So that would be 0.00 x. So that place right there. Okay, so 3 places out, that's plenty. And as you plug those back in, you come to y sub 5, and that is our approximation, right? So that is the estimate at the n equals 5 steps. So 5 steps out, we could keep going to continue to estimate. Our step sizes are incredibly small, so this is probably a pretty good estimate given using Euler's method. So there's just a lot of math here, right, to estimate those. This is a brute force method, just piece by piece, part by part. All right, so that is all that I have for you for fields and differential equations, and then one example for Euler's method there. I hope you enjoyed the video, and I look forward to teaching you on the next one.